Hello, everyone. My name is Arthur. I am a Mac developer at F-Secure, working on endpoint security products, and we cover quite a wide range of product engineering work, including starting from browser extensions and protecting our customers' activities online, and down to low-level things like malware interception and malware scanning. Yeah, and I can also give a word to Rasmus to introduce himself.
Yeah, so hi, my name is Rasmus Sten. So I work almost on the same team as Arthur, but I'm responsible for then the kind of like traditional anti-malware parts, file system interception, and kind of like behavioral protection parts of the product, which we call like the security platform, kind of like traditional endpoint protection features.
Yeah, so we will talk a lot about the macOS security mechanisms today, and the reason for that is because we are also interested in the similar triggers that mechanisms have for our own products. So we will start by covering what these security mechanisms are and why we are interested in them. And then I will cover my part of the talk, talking about one Gatekeeper bypass, quite recent. And then Rasmus will cover his one related to archive extraction. And a few final words in the end. So very quickly, the initial terminology, macOS Gatekeeper, so that's the main topic. So this is like the primary security mechanisms in macOS that is meant to prevent users from running untrusted software by producing like a lot of checks, code signatures, certificate validation, authorization checks, a lot of these things. But it, of course, is not applying these checks to all the files on the user's machines, but specifically to files with special metadata, extended attributes, and specifically one called quarantine attribute, which is indicating the origin of a file. So you can look at it by running xattr command or ls, and you will see, for example, where that file was downloaded from, or which application actually downloaded it. One more slide with that. So another important topic is launch services. So this is a system component or a system library which is responsible for keeping track of installed applications on the system. And it keeps track of like which applications can open which files. And it also manages all the, when there's time to make a decision which file needs to be opened with which application, then this is the lookup step during the startup. And the final thing that kind of combines launch services topic with the Gatekeeper is a special info.plist flag called LSFileQuarantineEnabled, and that flag instructs macOS to apply to quarantine files, all the files that the application touches. So that is, of course, handy for web browsers. So mainly they work with files which are downloaded from the internet. So it's very easy for the developer of the web browser to just set that flag and then let macOS handle all the cases when the quarantine attribute must be assigned to a file. Which leads us to the next topic, which is the discovery of the vulnerability. So here on the slide, we can see like a usual flow, how the things should look like on a happy day scenario. So a web browser, for example, Google Chrome here, download the file from the internet, and macOS should automatically assign a quarantine attribute to all the files, because as we can see on the bottom of the slide, Google Chrome has this info.plist key called LSFileQuarantineEnabled, and then macOS Gatekeeper can do its job and protect users in case that software is not intended to be run. And what happened in our discovery is that we noticed that the second step didn't actually happen. So the quarantine attribute was not assigned by a file downloaded by Chrome, which made us curious, and we started to investigate. And we initially reported it to Apple. This was earlier this year. Then we basically implemented a mitigation on our product side to better handle the situation where the quarantine attribute was missing on a file. And then Apple mitigated the issue in the report, in the new macOS update, and they contributed the report to us. Yeah, and apparently there were a couple of other researchers who also reported the same issue. A very brief demo just to make sure that we are not imagining it. So here we have macOS 13.2.1, and I'm downloading an unsigned application from my iCloud drive. And here, as you can see, there was no Gatekeeper prompt at all. So it was actually not an attempt to exploit anything. It was just downloading files from the internet. And just to prove that this is an unsigned application, we run code sign command, and we see that the signature is ad hoc. And if we actually directly ask Gatekeeper if the app is allowed to run using spctl command, the answer is no, it's rejected. But macOS didn't ask Gatekeeper, so that is why it was allowed to run. And of course, the fixed version, so 13.3 beta 2, so this is the version which fixed the issue. And here it works as expected, so not much surprise here. So we basically now have like 2 versions of macOS where we can explore more to understand what the issue was and how it was addressed. So first we decided to try and extract the system library binaries from the DLD cache. There are several tools for that. There was one that we found on GitHub, the DLD cache extractor, and we just decided to try and find any references in any system library that refers to LSFileQuarantineEnabled, considering that one of those components need to actually know about this flag and propagate this decision to assign the quarantine attribute. And so now we see that there are a few references to that flag, and one of those is launch services, and that is interesting for us because Apple also mentioned that they addressed launch services in the 13.3 release of macOS. So now Hopper time, so disassembler, we can load that launch services binary into Hopper, and we can see that there are a few hits, so a few places where that constant is used. And one of those is exactly the thing that was mentioned in the beginning, so it's just keeping track of all applications on the system. So this is like collecting information about the application and then sending over XPC to LSD, so the launch services daemon. But the second one was more interesting, so that was some sort of self-registration routine. So we, on the bottom, on the slide, we see that there is like a screenshot from LLDB, so this is like a breakpoint set on that same function which refers to the LSFileQuarantineEnabled. So the function is lsset_process quarantine properties. So this is according to the backtrace, so some kind of a registration routine. If we look at that function in more detail, we see that it collects information, so it creates some struct called qtn_proc_t, and then it forwards this information to libquarantine dynamic library. In the end, libquarantine actually invokes a syscall. So it just collects all this information about the application and sends it over to the kernel. So at this point, we don't know exactly how this data is actually used on the kernel side, but we know that macOS 13.2.1 was vulnerable, and 13.3 beta 2 was patched. So we can load the launch services binary into Hopper from both of these versions and compare how the function actually differs. And as we can see, there are 2 additional calls to a function called qtn_proc_set_flags. So we don't know much what is it, but these are new invocations in the fixed version of macOS. So at least this could be like accidental thing that Apple also included in the new release of macOS. But we decided to follow this trail and see what exactly it does. So we loaded libquarantine into Hopper, and we see that it's a pretty small function. It doesn't do much. So it just takes that qtn_proc_t struct and writes some value to an offset of 198. So probably it's an integer, but we of course don't know yet. And one interesting thing is that we see that in the syscall that was mentioned previously, it's passing the same data from the struct at offset 198 as one of the arguments, argument number 6 in the syscall. So At this point, we decided to switch gears to LLDB and set a breakpoint on the syscall function and see what actual data is passed to that syscall at argument number 6. So this is those mysterious QTN proc flags. And as we could see is that on the vulnerable version of macOS, it's passing value 0, and on the patched version, it's passing value 1, which is still quite curious. So we decided to follow this trail further. So our theory is that this was the way how Apple fixed it by making sure that the flags are passed to the kernel. But to prove our theory, we can do the following. We can go to the vulnerable version of macOS. So some of the sections of these are increased speed. So we attach a debugger to Google Chrome. We set a breakpoint on the syscall function. And we make sure that, yes, on the vulnerable version, it's passing value 0. So we just go ahead and overwrite it to value 1 to prove our theory that this is how Apple fixed it. We let it proceed. We download an app. We try to run it. And now Gatekeeper actually behaves as expected. So let's go to the patched version of macOS and try to break it. So we repeat the process, basically attach to Google Chrome, set the breakpoint, and then we make sure that the patched version of macOS passes value 1. Then we basically do the reverse change and set it to 0, let it continue. Google Chrome starts, we download the same application, we try to run it, and we are allowed to run it. So now we have like a confirmation that this was the place where Apple fixed the problem by making sure that the flags are properly forwarded to the kernel. So the argument number 6 was quite important in that invocation. One thing that we didn't cover in this talk now is the kernel side of things. Unfortunately, the kernel side was the most problematic during the research. Mainly because of the Apple provided tooling didn't prove to be very stable. So we tried to use the kernel debug kit to basically follow the same steps in the user space, but in the kernel to set a breakpoint and expect the state, but for some reason it was basically causing kernel panics and memory corruption issues. So if anyone has any advices on how to debug lifetime kernel in recent macOS versions, that would be super appreciated. And of course, there are 2 related topics. One being that this issue only happened when the app that is performing the action has the quarantine attribute assigned to itself. So if the same app didn't have the quarantine attribute, the issue didn't happen. And of course, the issue was not macOS Monterey, so the previous macOS version before Ventura was not affected by the issue. So there was a change in kernel between macOS Monterey and Ventura, which is still covered in mystery at this point. But we are hoping to uncover it in the future. But yeah, I think that was my part of the talk. I will give floor to Rasmus to continue.
All right. Oh, wow. Okay. So yeah, I found this vulnerability a couple of years ago, actually, but all the mechanics are still relevant and about the same in macOS Sonoma, so it's still very relevant, I think. So, but as you see from the title, it says a journey through archive extraction, quarantine attribute propagation along file paths. You can probably figure out exactly what I did here to find this bug. But let's talk a little bit about, Okay, so it was fixed in Big Sur and Catalina. Before Catalina, macOS was not vulnerable to this. So the discovery process then, it was basically it boiled down to a customer complaining to a UI bug to me that long file paths, they don't look bad in your UI. And I was like, okay, yeah, well, let's fix that. So the way to trigger that was that I created huge zip files and then I downloaded them and caused our product to react to it. So it showed the paths inside that zip file. But yeah, then I encountered all these weird limits when it comes to file and folder names. So files themselves can be 255 bytes long in their names. And then there's this constant called path max, which is 1K on macOS, I think 4K on Linux or something like that, which is basically the longest path you can pass to a syscall, not the longest path you can have. You can have very long paths. But I noticed, yeah, that in the deep end of this deep directory hierarchy that I created in the zip file, the quarantine attribute was simply missing. And as you know by now, the quarantine attribute is, of course, very important to Gatekeeper, but it's also important to our product, which is why I paid special attention to this. So at first, it looked like the cutoff was this path max magic constant, which wouldn't be exploitable because actually macOS refuses to just run any executable with paths longer than path max. It probably just simplifies a lot of things for them. So this is, I know, very hard to read, but this is how the zip archive looked in the end after I had created these very long paths. So at the top, you have the first path that is missing the quarantine attribute, and I found that, okay, this is 909 bytes long. And then on the bottom, you have the first one that doesn't have the above it, so that one was 894 bytes long. So it turns out that we have a sweet spot there that is actually shorter than path max, but we can still drop files that don't get the quarantine attribute. So this is really nice. And I know, kind of like through experimentation, I find that, okay, this is somewhere between 894 and 909. So this is like, I'm able to then, at this point, prove this by dropping an executable in there and running it in terminal, and it just runs. And okay, so this is a Gatekeeper bypass, but not that interesting because you're not going to get a user to actually like run this very like long path or executable in terminal. So let's utilize some other tricks to turn it into like a proof of concept that is like a reasonable exploit. So by default, Safari will unzip any files using its own built-in unarchive tool. And it turns out that when this happens, this bug is not triggered. It doesn't have this problem for some reason. However, it will also refuse to unpack archives with paths that are longer than path max, with no error message to the user. So we can craft a zip file that has both one path max long path that prevents Safari from unpacking it and therefore forcing the user or tricking the user into using archive utility instead. And then this like magic payload at the special path lengths, which we don't have the quarantine attribute. But then to make it actually like clickable for the user, we hide it into a .hidden folder, and then we make a symlink in the bottom pointing to the deep end of the .hidden folder. And this all looks pretty nice in the end. So this is how it's going to look when the user is. Let's see if it starts. Yes. So user goes to a website designed by ChatGPT. And then they're like, okay, yeah, here's a zip file. Oh, I'll just download it. I'll run it. And there's my app. And I launch it, and yeah, hello, I'm running. And I'll do the usual, just verifying that this is indeed an unsigned app. So this is on Intel, so it doesn't even have to be ad hoc signed. It can carry no code signature information at all. And if we look at this list here, we can see that that actually has the quarantine attribute, but that doesn't matter because the executable didn't. And then just for completeness sake, this is how it looked after the fix. It's just the expected Gatekeeper prompt. Well, let's just get it over with. Yeah, so this is how it's supposed to work. So, but what's interesting is, of course, why did this happen? So I did a root cause analysis somewhat. So first thing first is try to figure out, like, okay, what processes are involved? So I use a dtrace script. Nowadays you would use eslogger exec, but this was before eslogger times. So I used dtrace to find all the processes that were running during this time. So it will just list me all the processes that are executed. So I see a few different targets there, or the interesting things like archive service, AU helper service, and archive utility itself. Next thing I want to do is see what actually writes the files to disk, just to understand what's going on. And here we can see this, it's hard to read, I know, but it's this archive service process is the one that actually writes the files to disk, and I can see my crafted path names there, and how it actually chsteers to each directory and writes it there, so that it can create like arbitrary length file paths there. And here, one thing we can see there is the temporary directory it writes it into. So it turns out that it writes this into a temporary directory, and then once it's done, it moves it to its final destination. And herein lies the magic number, in that the temporary directory is a difference. The length in the temporary directory, it's much longer than the length of user's home or user's name download something. So there's a diff there, and that diff is what causes this problem. But we can dig a little bit deeper. So I want to see exactly what sets the extended attribute, the quarantine attribute. So I list all the dtrace probes with xattree in them. I create a tiny dtrace script that just prints the user space and kernel space stack trace when it hits these probes. And then I find this quite interesting function called qtn file apply to path implemented in glib-quarantine-dlib. So let's go there and see what's going on. So we can actually see then that to this function it passes a couple of arguments, and one of them is my file paths. So here it is, archive utility basically just trying to apply the quarantine attribute. And quite obviously, when we keep on stepping through this, eventually this path will exceed 1024 characters, because it includes this private var temporary folder. And then it will just fail at calling this. It uses also a special syscall to set the quarantine attribute specifically. It doesn't use the normal set xattr system library call. So let's then take a look at the thing that calls that. So this is the function that calls qtn file apply to paths. So this is the thing that actually iterates over the directory structure that has been created, and file by file applies the quarantine attribute. And it uses an API called FTS, that is a standard API that is done exactly for this purpose. You want to traverse a large directory hierarchy. And then it calls this qtn file apply to path. Okay, well, this is interesting, but what's actually going wrong here? Well, luckily we live in the future, so we can do the same thing on a fixed version of macOS. So I just basically now repeat my process on the fixed version of macOS, and we see, okay, there's a new process called AU quarantine service. So now they're not doing this quarantine attribute application in process, in archive utility, but in a separate service, a helper process. So if we put a debugger on that process, we can see that, here we have a function that calls qtn file apply to path, and now, okay, which function is now calling this? How does it look now when it's fixed? So we load up that up in Hopper, and it looks extremely similar. Of course, we can just side by side compare these functions, but we can experimentally also see what's going on. So let's get back to the debugger. And here you can see that when it hits qtn file apply to path, it doesn't have the complete path names anymore. It has this relative path name. So, problem fixed. But then is a question like, relative to what? Well, usually paths that are relative to the current working directory. So we're wondering, like, but what is changing the working directory? There wasn't any call to chsteer in that calling function that we had reverse engineered before. So I'll set a breakpoint on chsteer, and it's revealed that, okay, yes, this FTS library that they're using, it's actually calling chsteer for them. So that's pretty neat. So now we have the fixed version side by side. We can take a bit closer look and try to figure out, like, okay, something changed in how they use this FTS library to change from using absolute path names which break to relative path names which work. And what we see is that one flag has changed. It's this second argument to FTS open and also to FTS read there. And if you look at the FTS manpaint, you'll actually see that in the broken version, they had explicitly asked FTS to do not change directories. So the default behavior of FTS is to change directories and not have this problem. But they had explicitly instructed FTS, please do not change directories, give me absolute paths again, and give me problems with path max. But of course, in the fixed version, they removed that flag, and then everything works. So that probably also explains why they moved it into a separate process, because archive utility might have some assumptions or requirements on the current working directory not changing for it, because it's of course a process global state. So if you have lots of threads, that can cause problems. Yeah, so maybe Arthur can.
So yeah, a few words in final thoughts. So related to the first part of the talk, as we could see that quarantine attribute is quite important to macOS security, and we keep seeing these various aspects where it actually doesn't work as expected. So unless Apple rethinks this whole approach, we will keep seeing these different variations of the same issue where Gatekeeper is actually bypassed by missing quarantine or by some other condition. What that solution would be, we of course don't know, but it's something to keep in mind. And of course, yeah, as you could see, the issue was trivially, we didn't actually manage to, or had to try and expose it. It was just a complete accident that it happened. So it was super easy to replicate. So it's a good idea to actually actively test software against commonly used software on your platforms. So this is something that would have helped to prevent this becoming public and exposed to users. Yeah.
Yeah, and from my part, there were basically like two independent features contributed to this. So the handling of deep directory hierarchies, that's really the root cause here, is that operating system facilities for handling these and doing syscalls on them is awkward and error prone. You're gonna have to drop down in C, and yeah, you're gonna make mistakes. So you can fiddle around with, like, you can get a directory file descriptors and use openat and what that, but you're gonna make mistakes. So this is gonna be like very sensitive code. And a lot of things simply fall over in the operating system when they encounter long file names. So if you start experimenting with this, and I encourage you to do, I'm sure there's more interesting findings to do. Like, look at that, like, create long file names, just scan the system logs, you see errors everywhere. And some of those errors might be very interesting. In a way, this is like a time of check, time of use bug in that if they hadn't unpacked it in this temporary directory that had a different environment than the target, then this wouldn't have been exploitable. It would have still been an interesting and like probably like something they should fix, but that eventually was the final thing that made it exploitable. And yeah, this was kind of like a side project of mine, just a software engineer, so I didn't explore this in depth at all. Like, I just went through this exact code paths. There are many other code paths in archive utility and its helper process as you call Qt and file apply to path. So there might be many more vulnerabilities, and I don't know anything about it, but again, I encourage anyone interested to look into that and see how it works nowadays. Yeah, and especially these path max boundaries and similar boundaries, I think it might be interesting to explore those boundaries a little bit more and see if there are more bugs to be found there. And yeah, that was all we had actually, so thank you. And yeah, we have our blog post there.